Hi, welcome to this module. In this module, we will see monostable multivibrators. If you talk about a stable multivibrator, both state unstable. Now, if we talk about monostable, then one state should be stable, right. So, let us see what are monostable multivibrators. So, if you see this slide, monostable multivibrator, right, you can see it right over here, the circuit is shown here, right, has one stable and one quasi stable state, right. During the stable state, it remains in that state until a trigger is applied. Once the trigger is applied, the state is changed to a quasi stable state. Since this is an unstable state, it cannot remain for a long time and thus it reverts to the stable state till the next trigger is applied. So, as soon as it is a constant voltage, and when you apply a spike or a trigger, right, then it goes to the unstable state. Now, since it is an unstable or quasi stable state, it cannot remain for a long time and thus it reverts to a stable state. So, this charging and discharging of the capacitor in this case, right, provides the internal trigger signal. The circuit is useful for generating single output pulse of adjustable time duration in response to trigger signal. Whenever you apply a trigger signal, there will be a pulse generated. Okay. Now, width of the output pulse depends only on external components, okay, connected to the operational amplifier. The advantage of monostable multivibrator is it is simple in design and it is economical. The output of the circuit is perfect square wave, since the output is not concerned with the charging of the capacitor, that is the advantage, right. They are used as timers, or you can say it is used as timer, delay circuit, gate circuits, frequency dividers, etc. It is also used as a fixed duration pulse sensitive or to generate a fixed duration pulse sensitive to some external event to control the frequency of analog circuits output. And the use of this is to synchronize the line and frame rate of television broadcast, to regenerate old and worn out pulses in telecommunication and computer systems, and to moderate the tune of various octaves in the case of electronic organs. Okay. So, there the use of monostable multivibrator are many, as we have seen. Now, let us see how it operates, Okay. So, the circuit diagram monostable multivibrator circuit is using operational amplifier and its voltage response is shown here. This is the circuit, this is the triggering pulse, voltage response is this one, right, and let us see how this particular circuit works. So, in monostable multivibrator one state is stable while the other state is temporary state or quasi stable state. The permanent state may be either high or low. To change the state from permanent state to temporary state, a triggering pulse is applied. So, frequency of output will be equal to the frequency of input triggering pulse. The triggering pulse are obtained by differentiating a square wave, right. You can see here most of the circuit requires either a positive or negative pulse to switch. So, one type of pulse is eliminated and that is done by diode D1, right. So, we just require pulse which is either positive or negative, and one of the pulses can be easily eliminated if I use diode in this particular configuration. A negative triggering pulse is applied to the non inverting terminal at time t equals to 0. Now, you can see here this is the non inverting terminal, and at time t equals to 0, if I apply a triggering pulse, what will happen? Initially drop across capacitor C equals to 0.7 and the output is as plus V saturation, right. This is at 0.7 and that is why this is at plus V saturation, because the drop initially is the drop is this one and the output is at plus V saturation. As the triggering pulse is applied 0.7 volts, and if I apply this is plus V saturation, correct. So, as the triggering pulse is applied at t equals to 0, output changes to minus V saturation, right. If I apply here triggering pulse, then my output will change to minus V saturation. Diode becomes reverse bias, here it becomes a reverse bias, and capacitor charge discharging through the resistor, right. So, to minus V saturation. The capacitor charges until minus Vt and output changes to plus V saturation. Thus, the capacitor discharges through diodes, and so the time constant is very small. So, in absence of triggering pulse, the output voltage becomes back to its permanent state. The value of time constant R c determines the pulse width of rectangular pulse, right. So, you can see very clearly that the charging and discharging of the capacitor, right, when it discharges and it discharges through D1, it is very fast, and it comes back to the stable state. Whenever you apply a pulse, so this is a stable state, whenever you apply a pulse like this, it goes to its non-stable state, comes back and again stable, right, like this, goes back here, and in return the output will go to plus V saturation and minus V saturation. Whenever is here is minus V saturation, whenever it is stable plus V saturation, minus V saturation plus V saturation, minus V saturation plus V saturation. So, this is the generation of square wave. This square wave depends on whenever you apply a triggering pulse. The stable state is like I said Vd, and when you apply a pulse it goes to minus Vt, and since it is a quasi stable state, it will not remain for long time, it will come back to its stable state, right. So, in the absence of triggering pulse, output voltage remains back to its permanent state. The value of time constant R c determines the pulse width of the rectangular output. So, it can also be used as a rectangular pulse wave generator, right. That is another application of your monostable multivibrator. So, if I want to perform an experiment for monostable multivibrator, I will use this circuit shown here, and I will connect the circuit, select the resistance values and calculate the frequency, observe the output voltage and voltage across capacitor, and compare the output frequency with the theoretical results. So, what I will do? I will have a regenerative feedback, peak voltage across capacitor, output voltage and time period of output signal. So, again we will see how the monostable multivibrator can be designed in your experiment class. Okay. Now, to do that, the things that we have seen particularly about circuit designing, my TA Sitaram and Suman discuss about the circuit design and perform a simulation. Then they will discuss about how the circuit operates. We have seen in theory in detail, but we just need to have a quick recall of how circuit operates. So, they will show you about that circuit operation and compare it with the simulation. So, simulation we use multisim, and then we do not stop at simulation, we also go further and perform experiments. So, we will compare theory with simulation, we compare theoretical results with our experimental results. So, this is the complete idea, and now what I will do is I will request TA to join us and show us how the experiment procedure can be carried out, and I will request him to join us.
Now, we will look into a monostable multivibrator. In case of a stable multivibrator, we do not require any kind of a triggering input. So, once the power is on to the operational amplifier, directly the op amp gives an output square wave, and the frequency of the square wave entirely depends upon the charging and discharging rate of a capacitor. So, which is nothing but our beta value or beta into VSS value, that is nothing but your higher threshold and lower threshold values of our Smith trigger. In this case, in case if we want in our application, if we require to generate a pulse for particular duration only when we require at some triggering point, that means when I give a triggering point only then it should generate a pulse, then such a cases a stable multivibrator cannot be used. So, we require to have some kind of modification in the circuit, in the same similar kind of a circuit, some kind of a modification such that only whenever a triggering input is received, then it has to generate a pulse for a particular duration, for a particular frequency. Now, we will look into how this is called a monostable multivibrator. We will look into how the monostable multivibrator can be can give the output high for a particular frequency based upon the input triggering pulse and based upon the resistors and resistors that we use, resistors and capacitors that we use. And in this session what we are going to discuss is, one thing is brief explanation as we are following in the previous video lectures. In the same way, even in this module we will briefly discuss about a monostable multivibrator working of the circuit, then their connections, then we will see the theoretical calculations, then we will look into simulation, compare theoretical with the simulation, then with a practical results. So, as professor discussed in the module, so I may not go in deep into the complete explanation of the circuit. Now, when we go to the monostable multivibrator, so this is how the monostable multivibrator design is of. So, if you compare, we can see that the monostable multivibrator and a stable multivibrator looks similar, isn't it? And also even for monostable as well as for a stable multivibrator, the design uses a positive feedback, isn't it? Even our previous circuit, it has a positive feedback. That positive feedback, that means nothing but the resistors that we use in the positive feedback decides the value of beta, right. If we want to understand about the circuit, how exactly it works, recall our previous stable multivibrator. We understood that because of the positive feedback, because it looks similar to our Schmidt trigger, it gives some thresholds, positive threshold and negative thresholds. And since the output is connected to RC filter, right, and the junction of RC is given to negative, when our input voltage is greater than the threshold, then either it goes to plus VCC or minus VCC based upon the input signal. But the only difference that we observe in a monostable multivibrator is that along with RC filter there is one more diode which is connected in this fashion, right. Anode to positive and cathode to are ground. Now, so that what will be the implication of a diode in the system? So, one thing it is clear that whenever the output is positive, whenever the output signal is positive, in case the capacitor cannot charge to 15 volts, right. The reason is because of the diode. Whenever capacitor initially starts charging, once the value is equal to the cutoff value of D1, right. So, generally it will be 0.7 volts, right. Whenever it reaches to 0.7, then the diode will switch on, then the complete voltage will be connected to the ground. So, that means the capacitor will charge only till cutoff value of D1, right. Now if it is a case, when the output is at positive, it will never go back to the negative signal, right. Why? The reason is, when we see, imagine that initially we are getting V out as plus VCC, right. Only two states, either plus VCC state or minus VCC state. So, let us consider the V out, we are getting it to plus VCC state. So, what are the thresholds at this point? So, in order to go to minus VCC, the input voltage should be always, greater than higher threshold value VTH. In this case, what is VTH? Beta into R1 by R1 plus R2, right. Only when the input voltage is greater than this value, it goes to minus VCC. Now because of that, now if I say, we will assume that V out is plus VCC. If V out is plus VCC, the capacitor will charge, it will try to charge till plus VCC, but because of the diode, it will charge only till 0.7 volts. It will charge only till 0.7 volts, right. Since if this VA value, so that means VA will be equal to 0.7. Suppose if this VA value is lesser than VB, that means input voltage is lower than your threshold value, right. Threshold is nothing but VTH, which we have already seen previously, higher threshold value. If this value is lower than VTH, then diode cannot go to minus VCC, the op amp cannot go to minus VCC, it will be always at plus VCC. If it is always at plus VCC, the capacitor will be in a charging state. Because of the diode can only reach up to 0.7 volts. So, that is why when you look into the figure, we can see that whenever the output is positive, right, the capacitor charges till Vd, then it is constant. Now, when it goes to negative VCC, if the output has to go to negative minus VCC, the only condition is that the input voltage should be greater than our VTH. Now that condition will not happen until unless we give some external triggering pulse. What if I give some negative pulse at the positive? When I give a negative pulse at the positive, obviously the VA value is greater than VB. The condition is satisfying. So whenever I give a negative pulse, the VA value will be greater than VB. As a result, the output will go to minus VCC. When output goes to minus VCC, then since the diode will be in reverse bias condition, the capacitor will start to discharge till what? Till to our threshold value, isn't it? Why not to minus VCC? The reason is that we know that even from the stable multivibrator or even from the Schmitt trigger, when the input voltage is smaller than our negative threshold value, it goes to plus VCC again, right. So that means it will discharge only till minus VCC, right. So that decides right. So the complete frequency of this signal, but we will get the signal only when, right, this decides our complete frequency, right. Once it reaches to plus VCC, it continues the same what we have seen for the positive cycle. So this decides the complete frequency when to on, when to off. That entirely depends upon R and C, the charging value of a capacitor, and depends upon R1 and R2 values, right. But in order to get our negative pulse, the only thing is we have to provide one triggering input. That is why reason it is called monostable multivibrator. So and this complete the pulse duration entirely depends upon the equation, this one. The period is completely depends upon 2 RC log 1 by 1 minus beta, where beta is nothing but beta is R1 by R1 plus R2, right. That is what we are seeing even from our previous sessions itself. Now we will see how do we do our connections, and we will try to derive the theoretical, and then we will look into the simulation point of view. Now we will take a op amp, we will connect a plus VCC as well as minus VCC, right, with plus 15 and minus 15. So I am taking this as plus 15 volts and I am taking this as minus 15 volts, right. We will take a diode. So we will find out what is the diode cutoff frequency. So generally in a simulation we will consider diode the value is of 0.7 cutoff value. So whenever the capacitor reaches to 0.7, the diode will be forward bias condition. Whenever the input voltage is greater than 0.7, the capacitor value, right, the diode will be forward condition, then the capacitor will go to saturation. Then what values of R1 R2 we select? We select R1 and R2 as R1 as 10 kilo, as we have seen in the from stable as well as from Schmitt triggers. We are considering an R1 as 10 kilo as well as R2 as 10 kilo, right. So R1 R2 10 kilo, meaning the beta value. So we will say the regeneration factor. So this is 1. When I say regenerative factor, feedback factor, so I am considering R1 as 10 kilo and R2 as 10 kilo, so that the beta value will become R1 by R1 plus R2, so which is nothing but 1 by 2, which is 0.5 value, right. Now what will be the peak voltage across capacitor? The peak voltage will be equal to diode cutoff, so which is nothing but 0.7, right. So what will be the output voltage? Output voltage, the positive output voltage will be 0.7. Oh, this is output voltage. So output voltage will be always plus or minus VCC, because output can only saturate from plus VCC to minus VCC, but the period or the duty cycle depends upon our R and C, right. And what about the time period of the signal? So in order to calculate, so how to derive this particular value? So similar to that of our previous stable multivibrator explanation, what we can do is that we can consider this value 0.7 2 till this value and calculate the discharge time, discharge rate, and we can easily understand what is the time taken for this to discharge. And in order to compute our complete discharge as charging, now previous case we have considered from higher threshold to lower threshold. In this case you have to consider from lower threshold to Vd, which is nothing but 0.7. What is the time it takes? That if we can calculate, this gives us complete the on time, or this gives us complete time, right. And if I know at what frequency this is switching on and off, this complete frequency we can understand. Clear? So, this depends upon the capacitor value and the beta value, right, whereas this value depends upon when we are giving this peak. Now, so when we do the calculation similar to that of what we have done in a stable multivibrator, the T value, the period value will be equal to 2 times of RC into log 1 by 1 minus beta, 2 times RC into log 1 by 1 minus beta. So, where beta is nothing but 0.5, I can write it as 2 RC, right, into 1 by 1 minus 1 by 2, it is a 0.5, 1 minus 0.5, 0.5, 0.5 is 1 by 2, it is nothing but log 2, right. Now, what is the value of log 2? 0.693. So, it is nothing but, it is T is nothing but 2 into 0.693 into RC. Okay. Now, what values of R and C we will consider? We will consider R is 1 kilo and 1 microfarad, even in this case 1 micro and 1 kilo. So, the value will become, RC value will become 10 power minus 3 into 10 power. So, I can remove RC and I can write it as millisecond. Clear? Now we will see the simulation, how does it work, right, and we will go back to our experimental too. So, I will go with the simulation now. So, how the circuit will be? First, now what I will do is that I will go to op amp, I will select op amp, right, and I need to give the power supplies to that. So, I will go to DC voltage, connect negative here, then take a ground, connect it here, then go to another power supply, right. So, positive also I am connecting and taking ground, connect it here. So, the supply that we require is 15 volts. So, I will make it as 15 even in this case and even here as 15. Then what next? I have to take R1 and R2 resistors as well as R and C as well as the diode 2. So, I will place everything. This is, let us take this one as R1. So, this is R1. So, which has to be connected to the positive terminal. So, little bit down, then I will take one more resistor which is R2, which is a feedback resistor, that to positive feedback, and the both values should be of 10 K. So, I will replace this with 10 kilo ohms resistance, even this one 10 kilo. So, there will not be much difference between whether you take 10 kilo or 1 kilo, because as long as the beta remains same for the chosen resistor values, the system works similar way, right, and we require a negative feedback with 1 kilo resistors, which decides our charging rate of our capacitor. So, we also require a capacitor. If we do not have a capacitor, this complete stable monostable cannot work, because that entirely depends upon when to switch on, when to switch off, depends upon the charging and discharging rate of our capacitor. And we also need a diode, right. So, I will go with a diode and this should be connected in this fashion. So, we have made all the connections, we have put whatever the components that we required in order to build it. Now, what we have to do is we have to connect it. How do we have to connect? So, the output has to be connected to one of this terminal and other terminal has to be connected to the positive, and this terminal has to be connected to here, and take a ground, I will paste it here, right. So, the positive side which provides the Schmidt trigger operation, which decides the higher threshold value and the lower threshold value part is done. What is the next one? We have to connect RC charging and discharging to our output. So, I am going to this part, I will go here, I will go connect from here to here, and diode also has to be connected, right. So, what I will do, this part of diode I will be connecting it here. So, our circuit is done, right. Now, I want to measure how the capacitor, the charging and discharging decides, since we have a diode, and the output voltage. Okay. So, I will go to the grapher. So, let me check whether everything is right or wrong. D1, C1, right, 15, 15, 10K, 10K, 1K, 1 microfarad, D1 plus 15 and minus plus 15 and minus 15, yes. So, go to grapher and just run it. So, what is happening? So, which is red, which is green? Green is nothing but input. So, voltage across a capacitor, right, and this is output voltage. Now, see when we see the output across the capacitor, it is only 643.83 milli, which is approximately of 0.7 volts, right. That is the diode cutoff voltage. Now, in order to make it as monostable, I have to provide some triggering input at the positive terminal, isn't it. So, which makes the the positive terminal to go below, that means it makes the negative value is higher than the VB value, VA value will be higher than the VA value. So, that the output will goes to minus VCC. As a result, the capacitor will discharge from 0.7 volts to 0.643 volts to what you say, it is minus threshold value. So, what is the minus threshold value in this case? It is nothing but 7.5, minus 7.5 is the minus threshold value. So, how can I do? So, I can create any pulse. So, what I do is that I will take some DC voltage, some clock voltage, or some clock voltage I will do. Now, I need negative. So, what I will do is that I will reverse it. After reversing it, this I will be connecting it here, and this should be grounded. So, I am grounding it. So, since it is a 5 volts, I will get minus 5 volts as an output. So, if I want to understand, what we can do is that we can take one more voltage source and we can connect it at this point, and we can observe the blue color, the dark blue color. So, we can understand at what the value of it. Now, when I go to grapher and when I run the system, so for our understanding, what I will do is that I just stop it and I will zoom all voltage, then this I will make it as 100 milli. It is like zooming on x axis, or 10 millisecond, still zooming on x axis, or still more zooming. So, what is happening? So, this is nothing but our voltage across the negative pulse that we are giving, and the duty cycle of the pulse is 50% duty cycle. Now, but one thing we can see is that capacitor is discharging to till what value? It is not discharging to minus 7.5, it is discharging, but as long as it is ready to discharge, the pulse is becoming higher, meaning the pulse is going again back to the 0, right. Because of that reason, again the capacitor starts charging, again starts discharging. So, that we cannot expect the same thing whatever we require. So, in such cases, what we require is, we require whenever we give a negative, triggering pulse, it should on, or it should be a negative at particular duration of time, right, at particular duration, then it should go to 0. So, how do we create it? I need only a short duration pulse of minimum of 1 milliseconds, or even smaller than 1 millisecond. But with this, it is not possible, it will be keep on changing it. So, one way to do is that by using when a pulse connected to a differentiator, we will get a spike. I need only a spike. So, what we do is that we will create a spike. So, just to understand about how does it exactly works, what we do is that we will take this particular circuit. So, this if you observe the same input voltage that we are using it here, right, and now what we do is that at this point we will connect one voltage source. So, we can understand that what type of voltage we are giving, and we will connect one more output voltage here. So, I will remove this diode. So, just for our understanding right now, so how exactly it works, right. Now, let me run this and see the working of this particular portion. So, why we are doing it? We require only negative spike, and when the input is even becoming positive, I do not need to see any output, right, it still should remain the same, no influence on that. So, what I do is that observe here. So, I do not need the other two. So, I will make other two as 0. So, when we observe, so one is input, PR3 is input, PR3 is nothing but PR4 is input, right. So, the blue color is input and the pink color is output. So, whenever we have a spike, positive spike, so whenever we have a negative pulse, because of the negative pulse we are getting some spike, and again when there is a change from negative to ground, again we are getting a spike. But if I get this spike, there will be a problematic again. It allows the op amp to go to plus VCC state, but that should not happen. It should happen only when the capacitor is discharged to, or the capacitor voltage is lesser than minus 7.5 or lesser than minus VCC value, minus V lower threshold value. So, in order to happen that, this particular spike we should not pass through the system. How can we do that? One way is, if I use simple diode, what I will do is that this particular part I will connect it to diode. So, just to visualize this value, what we will do is that we will take one more resistor, connect across this. So, I just reverse this, connect this resistor and this particular portion to ground. Now, I will this particular portion to ground, connect it. I will take one more voltage source. So, we will check at this point. Now, I will go to grapher and in this case let me run. I do not need PR1 and PR2, again I am removing PR1 and PR2. Okay. So, what are all? PR3, PR4 and PR5. I need PR3, PR4 and PR5. PR1, PR1 I do not need it. So, when I zoom this, just off, when I zoom it, this is the input signal blue color, right. So, blue color, when you see blue color is input. Now, output from the differentiator is PR4, pink color. Now, when I remove both the things, we can see that now it has given only a positive, only a one spike, right. So, whenever this spike is there, then it allows VB, right. It makes the op amp to be at minus VCC. The reason is that the VA value, that means the voltage across negative terminal is higher than the voltage across your positive terminal. So, whenever that happens, the op amp goes to negative VCC, right. So, this is okay since it goes to negative VCC. Now, once it goes to negative VCC, the influence of the input is not there to the op amp circuit. As a result, when the capacitor is below minus lower threshold value, till that time the output will be at minus VCC. Again, if it happens, it goes to positive VCC. Now, we will connect this particular circuit by replacing this with this. So, what do is that we will select this complete part, move from here to here. So, now already I have a resistor, I do not need any of this resistor here, this is just for a load resistance, and this value has to be connected here. So, I am connecting it here. Now, if I run the value, have a look. When I zoom the value, right, we can see. So, whichever is not required, I just remove it. So, I do not need, we will see one by one. This is my input, voltage across the capacitor meaning, and this is output voltage, and the PR3 is the pulse that we are giving, PR4 is the output across that across differentiator. Now I do not need it, right, but we can observe one thing, that when I give a spike, till I give a spike, the negative voltage is at somewhere around 664 millivolt, which is almost equal to 0.7 volts diode cut-in voltage, right. Whenever I give a negative spike, the blue color one is a negative spike for somewhere around 10 milliseconds, right. So this one, since it is passed to a differentiator, it has generated one positive spike of 10 milliseconds, sorry, it generated a negative spike. Because of this negative spike, the VA value is greater than VB value, the voltage across VA is higher than the voltage across VB. So it makes the output of op amp to go to minus VCC state, we can see here minus VCC state. Then what we did? So what we did in a sense, then how it is going to plus VCC again, because of the negative volt, because of minus VCC, now the capacitor starts discharging to minus 15 volts, right. Now the capacitor started discharging. Now since the threshold value is 7.5, when you observe that minus 7.5, whenever the VA value is reaching below minus 7.5, that is our lower threshold value, then it makes this particular value to go to plus VCC, output to plus VCC, that is what we can see, right. So when you observe this value, so we can take the cursor, x axis cursor, and when you see what is the time duration to go from this, and when you calculate based upon that, and the value is somewhere around, okay, this value, right, cursor to somewhere around 7.5, okay, somewhere nearby. So the value, the on time is somewhere around 6.8259 milliseconds, right. So this is the on time, whereas the complete cycle, if I see from here to here, sorry, this is off time. So we can see 100.26. So this is the case when we use 10 kilo ohm resistor. So what happens if I use 100 kilo ohm or 50 kilo ohm resistor higher value? Since it is a 50K, the discharging rate will be little slower, because the load value is smaller, so it takes lesser time to discharge, so more time to discharge it. Since it takes more time, we can see the change in the width, this particular width. Now this should increase, because the capacitor will discharge very slowly, right. So right now the value is somewhere around 6.8 milliseconds. Now it will be even more. So what I will do is that I will replace this 10K with 50K resistance, 50K, and we run it. Now when we look into the graph, see, observe what happened. Now the width, this cycle may be same, but the width of this changed, the duty cycle of your pulse is changed. This is because of the capacitor discharge rate is different compared to the capacitor the capacitor discharge rate of the previous resistance value. As a result, the discharge rate is smaller in this case because of a higher resistance value. It makes the output to stay at minus VCC for a longer duration. That duration you can calculate based upon your RC discharge time. So whatever we have seen, whatever the calculations we have made during a restable module, whatever we have calculated, if you do the same calculation, we can even see the voltage from here to here, right. Or if you want to compare, what we can see is that I can put one value at here and one more. So previously, if I remember right, it is a 6.9 millisecond. Now if you see 37.5 milliseconds. What if I decrease my resistance value? If I decrease my resistance value, it consumes a lot of current, so that the discharge will be little faster. So, faster the discharge, faster the ramp, right. It discharge somewhere here, even lesser than 6.9 milliseconds, if you can say 6.9 milliseconds, right. So, depends upon when you provide a triggering pulse. If I delay the triggering pulse, so if this triggering pulses the frequency is a little higher, right, we will get different frequency again, right. So, it entirely depends upon when you give a triggering pulse. So, that means a monostable multivibrator, what we can see is that it is not continuously generating sinusoidal a square wave signal, but the user has to provide a triggering input to the system, only then it goes to the minus VCC state. Then once it goes to then when the capacitor starts discharging, whenever the voltage value is smaller than minus reference value, again it goes back to its original state. So, till next triggering pulse received, it will always be at that particular state, right. So, you can even change the different values of resistance, and you can even observe that. So, or even you can change the capacitance value no matter what, because RC entirely depends upon R and C. So, the multiplication factor is what are responsible there, and I hope it is clear why we have used this differentiator. So, the purpose of the differentiator is the square will be converted to spike, which is a triggering input, and the purpose of this diode is, since when you do a spike will happen even at a positive pulse, whenever change in the whenever there is a change in amplitude from 0 to 5, 5 to 0, I mean 0 to minus 5, minus 5 to 0, whenever this happens we will get a spike because of the differentiator, right. When you differentiate a pulse you will get a spike, right. So, since we do not need any spike at the when the ramp is, when the input is going from minus 5 to 0, if you use a diode, so which will block all the positive signals, right. So, we will get only one spike during the negative pulse. So, this negative pulse will responsible to discharge my the discharge your capacitor till it goes to minus VCC. As a result, we can see the period complete signal. So, what we do now is that we will develop the same thing using our TI board, and we will see whether we got the whether we are getting the same thing or not. Now, when we look into the TI board, so when we look into the TI board, right, so this is our TI board, right. So, even in this case we are going to use this particular portion, right, as we have already seen in the last time. So, we will connect in a similar fashion, so all the diodes and everything, and we will see what response we get, as we have seen even in simulation, right. Later on we will connect input source, we will see how the response will be, then we will connect triggering pulse, that differentiator everything, and we will see the response of the system, right. So, we will disconnect the previous circuit. Okay. So, the previous circuit is a stable multivibrator. So, we do not even have to disconnect everything, the wirings are everything same, only thing is across our capacitor we have to connect a diode. So, now we are taking a diode. So, that is our capacitor. The capacitor that we use is 1 microfarad there. So, we can see across the capacitor right, we can see here we have connected right. So, how the connections are to the ground, the cathode is there, and other side it is connected to positive like a negative terminal of our this is going to the negative terminal of our operational amplifier, right. So, this is as per our circuit now. Now, what we have to do, now we will switch on the circuit. we will see what is the response that we get in our oscilloscope. So, we do not need any input in this case. Why do we do not require any input? Because this is an stable multivibrator, it should automatically, or monostable multivibrator, since we are using a diode. But since there is a diode, it cannot go to the other state, meaning the input voltage, when the output is positive, the voltage across the capacitor will be at 0.7, right. We can even see. So, here when we see the signal, the blue color indicates what? Our output, right. So, the scale, if I see, when you see the scale, this is at 1 box is equal to 5 volts. So, when we look into the scale, so 1 box is equal to 5 volts. So, if we zoom into the oscilloscope, right, the second one is 5 volts, and whereas the first one, which is yellow color, the box is of 500 millivolts, one box is 500, right. So, that means the voltage output is of somewhere around 15 and the input is 0.7, that means the voltage across the capacitor, the yellow is voltage across the capacitor, which is, so we are aligning both the things to the same point, so that easy to understand. So, the blue color one is 5 volts, we can see here. So, we can see this is 5 volts, and whereas this one is 500 millivolts. So, that the blue, that which is nothing but output, so it will be 5, 10 and more than, it is somewhere around 12 point something, whereas the output if I see, so that means it is already at a positive VCC. What about the output? Output is somewhere around 700 millivolt, right. So, that is our cut in voltage of our diode, right. So, when I take a diode will be always at cut in voltage, that means it is not allowing the capacitor to charge more than 0.7, the voltage across the capacitor is 0.7. Now, since it is at 0.7, it cannot go to the negative state. If it cannot go to a negative state, again it cannot discharge it, right. So, the capacitor is always at this stage until unless when we provide a negative triggering pulse. So, what we do is that in order to generate a negative triggering pulse, we will take a function generator, we will generate some pulse output. So, we will generate from pulse output. When we look into the function generator, so we will take the same frequency, 10 hertz frequency we will take, and the duty cycle as 10%, 10 hertz frequency, and duty cycle as 10%. But we need a negative pulse, but it is giving a positive pulse. What we can do is that, so we can create an offset, and amplitude is of 5 volts, we will take 5 volts peak value, or since we have given peak to peak, we can say offset as minus 2.5, sorry, offset as plus 2.5. So, we will create an offset 2.5 volts. So, we can see, okay, we got 5, but we need a minus 5 positive input terminal, we will connect it in a reverse way. So, when we see the connections, so now we will connect it. We will switch on the output of function generator. The negative pulse of, so the negative terminal of the function generator, we are connecting it to the positive terminal, the junction or positive terminal of an op amp, and the positive terminal we will connect it to ground. Right. So, we made a connections now. What is the response we are getting? So, we will make it auto scale CRO, right. So, what we do is that we will create same differentiator even here, we will create same differentiator, and we will try to provide a spike as an input to the system. So, we will switch off everything and we will provide, we will give, we will connect a differentiator circuit on the breadboard, on the breadboard of our TI board. So, what values we will take? We will take 2.2 K and 0.1 microfarad capacitor. So, we are connecting 2.2 K resistor on the breadboard. So, the input should be connected to this particular point. So, that is the reason, right. First is capacitor, then resistor, right. This is a differentiator circuit. Now, we will take 0.1 microfarad capacitor, right. So, we made a connections. So, that capacitor value is 0.1 microfarad capacitor and the resistor that we are using is 2.2 kilo ohms, sorry 2.2 kilo ohms. So, 0.1 microfarad and 2.2. So, what we do is that the input from function generator, right. So, the negative should be connected because we require a negative spike, negative should be connected to the capacitor and the positive should be grounded. So, now if you observe, the ground is connected to the other part of a resistor and the white color wire, which is the ground of our function generator, is connected to the capacitor input. Now, we will observe what is the response we get. So, we will take the two probes of the CRO and we will connect one at the input, other one at the input of the capacitor, other one at the junction of capacitor and the resistor wire. Since it is a passive differentiator, we may not require any supply voltage to this. So, we can see that the red color wire is connecting to the input, right. Now, we connected one channel positive input to at the capacitor place, the capacitor input, the ground will be connected to the reference value. Made the frequency as 10 hertz, high level to 0, low level to -5 and the duty cycle to 90%. So, since it is 90% duty cycle, so on time is more and off time is smaller, and directly since the low level is -5, so -5 on time is little smaller, right. So, this is connected using this BNC probes to the input of the capacitor at this point. So, we have connected to this point, observe, we have connected here, right. The positive is connected there and the negative is grounded, the negative wire is grounded to this point, and one channel of oscilloscope is connected here. This is the first channel of oscilloscope connected here with a positive one, whereas the negative terminal is grounded. So, this is the negative terminal where both the negatives, oscilloscope as well as function generator, is grounded to this particular point. Then another channel, oscilloscope another channel, the positive input is connected at the output of junction of our resistor and capacitor. So, this is the junction of this is our capacitor 0.1 microfarad, right. This is resistor at this junction, whereas the negative is grounded. So, when we look into oscilloscope, when we see the oscilloscope, we can see that both channels are at 5, but you have a little offset in the second channel. But one thing we can observe that the input is negative for duration small percent, that percent is 10% if I consider a negative side, if you consider with respect to the positive side it is a 90%, right, and going again higher lower. So, since this signal is passing through a differentiator, we are getting a spikes. When I zoom it little more, right, whenever there is a change in the change from 0 to 5 or 5 to 0, we can see the spike. Because of the negative changeover, you get a negative spike. Because of the negative to 0, we are getting a positive spike here. But we require only this spike when we are giving a triggering pulse as an input to our monostable multivibrator. Otherwise, if we pass even the signal, it again comes back to the previous stage, which is unwanted or unnecessary in our case. So, how do we avoid this signal? Since we do not need this particular signal, what we do is that we take a diode we connect this particular we connect a diode such a way that it will pass only the negative signals and the positive pulses should not pass. So, we will connect it in the cathode output. So, we will take a diode, and this diode we will connect it to the cathode of the diode will be connected to the junction point, and we will connect anode to the positive terminal. So, positive terminal in the sense, so I will take another wire and I will connect both the things. Or this particular terminal I will use some buck connectors and connect it to the positive terminal, right. So, this terminal I am connecting it to positive terminal, right. This is what we require. Now, when I measure output across this point, and when you look into the oscilloscope, okay. So, what we do is that this we will see the complete output voltage. So, output voltage should be, so this is our output voltage, we will connect it. So, we can see from the oscilloscope it was very small. So, what I will do is that I will change this 1K with the 10K resistance. And let me switch on the main. So, since it is 15, what I do is that both to be at the same point. Okay. The second output channel as well as input channel I am keeping little down, and let me zoom little bit, right. Let me stop, and here we can observe that right whenever there is a okay. Since we have not connected across a capacitor, but if I connect the input the yellow color to the output across a capacitor, so we can even see the response with respect to the capacitor change. I am connecting across the capacitor, right. So, what we can see, the capacitor is somewhere around 5 volts. So, 1 volt is somewhere around 5, right, or I can take a cursor and channel 1, okay, channel 1 type amplitude. So, I will make it 0, I will take the cursor. The value is somewhere around 1.8. So, here we can observe that whenever we are giving a negative pulse, right. So, what is happening because of this negative pulse, because of the negative pulse from the function generator, the capacitor starts discharging, right. So, whenever it goes to minus 7.5, then it goes to minus VCC. So, it is going to the minus VCC, and again when the value is greater than 7.5, it is again going back to the plus VCC, and this spike we can see because this is the voltage we are observing before the diode. When we pass through after the diode, even that we cannot see, right. So, when we measure this value, when we use a cursor and when we take cursor type is of time, and when we take with this. So, the value is somewhere around 500, the difference between is 800 microseconds. So, you can compare these results with our simulation results and we can verify it. So, that means we can understand that in order to generate a triggering pulse, until unless we generate a triggering pulse for a monostable multivibrator, we cannot see any change in our output because of our diode, which makes the capacitor to go to stay at 0.7 volts, which will not allow the capacitor to charge more than that. Since it cannot charge, the output voltage, the voltage across the VA, which is nothing but negative terminal, is smaller than that of higher threshold value. As a result, the output will be always stays at plus VCC, right. So, in order to make it, when we provide a negative pulse, then the VA value is higher than the higher threshold value, making it the op amp to go at minus VCC level, then the capacitor starts discharging. So, because of the discharging state, the output will be at minus VCC until when the voltage across the capacitor is below the negative threshold value, it will be always at minus VCC. When the capacitor voltage is even below 7.5 volts, minus 7.5 volts, then it goes back to plus VCC state. So, till then it will be always at minus VCC. So, that discharging rate is responsible for the time duration at which the the output voltage will be at minus VCC, right. So, this is the difference between an stable and monostable multivibrator. Thank you.